So our last sub-lecture on metamorphic rocks is going to focus on different types of deformation that can occur on rocks. And we're going to break them up into brittle deformation and ductile deformation. Before we talk about that, though, we want to talk about a couple of terms that may come up. So when we are mapping geologic structures, like deformational structures, like big folds or big faults, we have to be able to measure and describe the orientation that the layers of rocks take. And that's what we use strike and dip to do. So if I say it verbally and then I show you diagrams, I hope this will stick just a little bit. Strike is the compass direction of a rock layer as it intersects a horizontal surface. If you took a slanted section of rock and you figured out how to walk across that section without going up or down slope, you would be walking along its strike. We'll look at what that means in a second. Dip is the other direction. It's the amount of tilting that the layer has, and it's measured at a right angle to strike. So if you were to walk straight up or down that tilted rock surface, you would be walking along its dip. And you could describe the steepness of the dip using an angle. Let's think about this in terms of our roof first. So if you had some roof, you could describe its strike and dip. The strike would be the direction along which, if you walked along that roof, you wouldn't go up or down, right? So its strike here is this way. And we can measure it with a compass. So, right, if this is north, then the strike of this roof is east-west. This is the direction that east points, and that's west. So this is the strike. The dip would be first the direction in which the rainwater runs, which is perpendicular to that. So the dip would be to the south. And then we could measure its angle with the horizontal, right? So if this roof is pretty steep and it's like a 45-degree angle here, we could describe that as a dip of 45 south. We can do the same thing with rock layers. So if we have, especially sedimentary rocks, but really any kind of rock that has any sort of layering to it, and we look at that layer of rock, we can figure out what its strike is by measuring along that surface, and then what its dip is by measuring what direction it dips downward in, and then also the dip angle. So you've seen strike and dip now. These kids are running along this rock. And if they're running along in this direction, what are they running along, the strike or the dip? Well, they're staying horizontally at the same level. So this is the strike here. And then the dip would be in this direction with some angle. So you might describe these rocks as dipping shallowly towards the cliffs. And if you had a compass, you might be able to tell what direction that we're pointing in. Okay, now let's get into our discussion of deformation. Deformation, or things that deform rocks, change their shape due to forces. They are mainly going to occur near plate boundaries, places where the plates that make up Earth's surface push together or slide past each other. By observing deformation in the field, we can use that information to help us reconstruct geologic history. These are other events that we want to piece together because they tell us things like when ancient continents formed and such. If you have rigid rocks that are relatively solid, right, and that deform in a sort of solid way, if you deform them, you will fault them, you will break them. Other rocks that are a little bit softer, you might be able to fold. If a rock can be bent and you deform it slowly, you'll end up folding it instead. And folding and faulting are the two types of deformation that we talk about most often. Okay, so we will talk about tectonic forces and the directions in which those forces move, tensional, compressional, or shearing forces. And then we'll talk about whether they produce brittle or ductile deformation. Do they fold or do they fault? Before we get onto that, I'm going to give you a little diagram of what each of these terms mean. So if you put tension on something, if you take a string and you put it under tension, what are you doing? Well, you're pulling on both ends of it. So tensional forces are pulling apart forces. Compressional forces, if you compress something, you're pushing on it, right? So that compressional forces are those forces that are pushing together forces. Shearing forces, this is probably a little less familiar. But if you have two, blocks or whatever, and those blocks are sliding past one another, that's shearing forces. So sort of in between pulling and pushing, right? Instead of pulling or pushing, if you slide past, then that's shearing forces. Those are the forces that you get when you rub your hands together really fast to warm them up. Those are shearing forces. In terms of these terms down here, brittle deformation means breaking. If you've ever had peanut brittle, that's because the peanut brittle you can snap into pieces. Ductile behavior is bending behavior. If you put a force on a rock, whether it's tension, compression, or shearing, depending on a few different factors we'll talk about, you could get the rock to break or you could get it to bend. So this is a cylinder of undeformed marble, and we have subjected it to an experiment where we have tried to deform it in a brittle way and in a ductile way. So what we find is that if we subject it to conditions representative of the shallow crust, so like low temperature, especially, and low pressure, the rock breaks if you put force on it. So these are places, these cracks in it are places that the marble has broken, which shows us that it is deformed in a brittle way. There are individual planes along which we can pick that rock has broken as it's been pressed. Now, strangely, if we do it in conditions representative of the deeper crust, so we have a higher temperature and a higher pressure, if we deform that same rock, we will deform it in a ductile way. You don't see any individual cracks in this rock, at least, very few, maybe one there. But for the most part, it looks like this rock has deformed all at once and it's sort of bowed outward without cracking in any individual spot. And we would call this ductile or ductile. So brittle deformation is breaking, ductile deformation is bending. What factors favor brittle breaking versus ductile bending? Deformation. Rocks will tend to behave in a brittle way if they are deformed quickly, right? What we might say a high strain rate. So if rocks push together fast, then they will tend to break in a more brittle way. Earthquakes are an example of brittle deformation occurring in Earth's crust. It happens quickly and rocks slide past each other. They break, they shatter along fault lines. That's brittle deformation. It's also favored by low temperature or low confining pressure. So you tend to get a little more brittle deformation near Earth's surface. Ductile deformation, if your motion is very gradual, you do it slowly over time, you have a low strain rate, we could say, then you will tend to bend rocks more than break them. It's also favored by high temperature and high confining pressure. All of these favor ductile deformation. And so this deformation, since it's a higher temperature and pressure, it's more likely to happen inside, deep within Earth. But that's not all. Mineral composition also has an effect. So certain rocks are more subject to brittle or to ductile deformation, depending on the minerals in them. Here are some examples of brittle deformation. So these are faults, breaks in the rock along which the rock has slid. Here's one, here's another one, here's the 90s man. These faults, we have had motion. We can tell just by looking at the layers of rocks that they have been displaced. We can imagine if we wanted to restore this rock to its original shape, we would want to move this dark layer and move it back up so that it's in line with that. And then this white layer would also line up, and this thick brown layer would also line up. And so by looking at this, we can tell that this body of rock here must have moved down and to the left relative to this body. Either that or this one moved up and to the right. We can't tell which, so we put both sets of arrows on here. We'll be able to tell which in a little bit, but when we draw these faults out, we will draw both arrows to suggest the sense of motion of that fault. We can tell that it's brittle deformation because the rocks have snapped and moved. We don't have a big bend in the rock. Instead, we have a clear plane along which that rock is broken. So we consider it brittle deformation. We can talk about different types of faults, and these will come up at various points. So we should learn some some terminology. 3 types of faults that we'll talk about are normal faults, reverse faults, and thrust faults. And then we'll add in a couple more in just a second. Normal faults are created by tensional forces. Reverse and thrust faults are created by compression. And we can tell that by looking at the way that the rocks have moved. Normal faulting takes a rock and it pulls it apart. But instead of creating a gap, what will tend to happen is one wall of that fault will slide down, which has some component of motion away. And then one will slide up or stay where it is. But there is a component of those motions that is apart. For reverse or thrust faulting, if we look at those same rocks, we will see that there's a component of the motion that is actually pushing together. If we break that up into 90-degree motions, those motions push together. And that's how we can tell that these faults resulted from compression. If we're just looking at a fault out in the field, we will often think of it as having a hanging wall, a wall that hangs over the other one, right? Like this shape is sort of hanging over, and the footwall, which is, some people have told me that they feel like this is shaped like a foot, right? That's a terrible drawing of a foot with somebody's toenail there. But this footwall sits under the foot of the other wall. Just looking at the angle of this is the hanging wall. This is the footwall. I'm going to clear these, make it easy to see. Hanging wall, footwall. The hanging wall is hanging over the top of the footwall if we look right here. When we find a fault where the hanging wall slid down relative to the footwall, that's how we know it's a normal fault. If we find a place where the hanging wall, which is still this one or this one in that case, slid up relative to the footwall, we know those are reverse or thrust faults. The only difference in between reverse and thrust faults is that reverse faults have this very steep angle to them, and thrust faults have this very shallow angle. This is the angle I'm looking at. It's a steep angle. This is a shallow angle. So that's the only difference between reverse and thrust faults. The thing to remember is that normal faults are created by tensional forces, by pulling forces. Reverse and thrust faults are created by compressional forces. And if you look carefully at how the rocks have moved, you can tell that. Normal faults have moved apart a little bit. Reverse and thrust faults have pushed together a little bit. What about shear forces? They create strike-slip faulting. Sometimes we'll call them transform faults as well, but really only when they occur in certain spots. We'll talk about a little more when we talk about, or maybe you've already talked about it, when we talk about plate tectonics. These are places where rocks have just moved horizontally relative to one another. Those types of motions we have drawn there. So we could say we have some hills here. Those hills have been displaced to the left if we look across the fault here, right? Because if you're a person standing on top of this and you looked this way, you would look for your hill and you'd have to look to the left to see where that hill is today. That's why we call these left lateral strike slip faults. If you looked from the other side, you looked across, that hill from your perspective here, it's still to your left. Kind of funky, but try to wrap your head around that. Left lateral strike slip faults, they will look left lateral whichever way you look. And it means that if you look across the fault, stuff has moved to the left. In contrast, right lateral strike slip faults have stuff that has moved to the right when you look across it. I'm looking for that hill that I was standing on, and I would have to look to the right. From here, you'd look across, you'd have to look to the right to see that hill. Both of these, left lateral or right lateral strike slip faults, they're both created by shear forces. So you've got some faults that are created by tension, normal faults, some faults created by compression, reverse and thrust, and then some faults that are created by shear forces, strike slip faults. These are all types of brittle deformation because rocks break along a single plane. Joints in rocks are places where the rock has broken, like this joint here or there or there. Those are just breaks in the rock where you've had no motion occurring. Joints are planes along which it's easier for water to move. And so as a result, that water can get in and it can weather these rocks. So a lot of times if you have jointed rock, it will start to weather. And that's how we've generated these rounded spheroidal weathering patterns here. So those are both types, joints and faults, are types of brittle deformation. Now we will talk about folds, ductile deformation. And the two types that we mention most often are called synclines and anticlines. And they often occur right next to each other in sequence. That's because if you were to say fold, if you took a bed sheet and you scrunched it up, there are some places where it folds upward and some places that it folds downward. And those are what we mean by anticlines and synclines. Anticlines are places where the fold is upward. Synclines are places where the fold is downward. And if you were to fold a bed sheet or a rock by just rumpling it a little bit, you know that those have to occur relatively close to one another to accommodate all of that folding. So here we've got like an anticline, then a syncline, and then another anticline. And on the other side, here's a syncline and an anticline. How do you remember anticline versus syncline? I like to think of anticlines are the ones that are shaped like an A, and synclines are the ones that are shaped like a smile. The simplest type of fold is just a horizontal fold. Its axis, if you were to walk along the surface of that fold, you would stay at the same level. You'd stay horizontal. But you can also have something called a plunging fold, where that fold, and not only is it folded, but that fold also dips into the ground. Both of these, though, synclines and anticlines, and whether they're horizontal or plunging, they are types of ductile deformation. They're folds. Here's an example of ductile deformation in this rock here, where the rock layer used to be just continuous all the way across, but it has folded in this direction and in this direction here. Remember that anticlines fold upward into an A shape, synclines fold downward into a smile shape. And one thing that many introductory students think is that anticlines must form hills and synclines must form valleys. But remember that these things probably formed deep underground long ago, and that since then, erosion has had time to do all sorts of weird things to Earth's surface. And so anticlines are not always hills. Synclines are not always valleys. It depends on how resistant the rock is at the surface. One thing that you can tell is if you look at, say, a syncline, and if you were looking from up above, we learned based on our Steno's laws, our laws of stratigraphy, that rocks that are on top are generally younger than rocks below. If you took a syncline and you were looking at it from up above, the youngest rock ends up being in the center of a syncline. If you were to erode away, it's not great to see in this diagram, but if you eroded away the top of this anticline and you were just looking at the surface, it's actually oldest rocks are at the center of an anticline. And that way you can tell whether you're looking at an anticline or a syncline. If you know the ages of the rocks, you don't even need to be able to look at sort of a sideways view of these rocks to tell. So here we see a bunch of different deformations going on, but the ones that seem most obvious to me, we've got some folding down here that we can look at. We've got some folding here, the general trend of these, and we can see how these anticlines and synclines end up coupled together. They can reveal themselves in very dramatic landscapes like this one. So we had already brought up plunging folds briefly. They are folds that also dip, and they tend to look like a if you look on the surface, they tend to look like sharp U's and V's, and the resistant rocks are the ones that make the hills. We see that, or things similar to it, throughout the Ridge and Valley province, of which Tennessee, East Tennessee at least, is a part. So if we look at just down at the Knoxville area, right? So here's 81, here's I-40, Smokies are over here. This area, if you look at it from satellite view, you see a bunch of parallel hills that are still covered in trees because it's hard to build on hills, and valleys, which are much easier to farm. So they were cleared first, and they are still left more exposed than the hills are. You can see these parallel hills all continuing in the same direction, parallel to the front of the Smoky Mountains. This is what's called the Ridge and Valley province, and it extends in our area from the Smokies in the east all the way to the Cumberland Plateau in the west, where you no longer see those same sets of hills being all parallel to one another. Instead, you see that they're sort of highly dissected. You can see this sort of what we call dendritic stream patterns here, but there's not a lot of folding that's present in these rocks. So the Ridge and Valley province is a series of folds and faults squeezed between the Great Smoky Mountains and the Cumberland Plateau. And so you can see that series of different hills. And if you were to look at those rocks, you'd realize some of them are folds and some of them are faults, with the most resistant to weathering rocks expressed at the surface, sticking up as the hills. If you were to continue all the way up into like through Virginia into Maryland and Pennsylvania, you get to a section that looks similar to ours in Tennessee, but it's a little more mixed up. You can see some of these hills, like they seem to sort of terminate in these sharp U and V shapes. And that's because there are a lot of plunging synclines and anticlines, plunging folds that are making up the folded rocks in this area. I will note that if you're observing metamorphic rocks, right, that means that they were probably buried at some point, but then they have later been back up, brought up to Earth's surface somehow. That means that they have to somehow be unburied. Tectonic forces can help push them up, but for a large part, for you to see metamorphic rocks, they must have been unburied by erosion at some point. I want to bring that comment up now so that you think if you see a metamorphic rock, it must have been buried and then unburied. Let's combine some of this stuff on deformation with our information on Steno's laws, those principles of stratigraphy that we have learned when talking about sedimentary rocks. And these laws can be used to interpret the order of deformation events and depositional events all together. So we could look at this block diagram down here, and without any other information other than Steno's laws and the fact that we've got some folding and these red lines are faults, that's why the rock is broken along those, we can use that to piece together the order in which these rocks formed. So see if you can figure it out by looking at this. Pause the video and think, can you figure out the order in which these events occurred? There are 3 rocks that got laid down, a black basalt at the top, a tan sandstone with planar bedding here, and a gray siltstone down here. There are 3 events you should be able to piece together too: folding, faulting, and erosion that created an unconformity of some kind. See if you can look at this block diagram and figure out the order in which those events happened. Okay, let's talk about it. Well, the rocks at the bottom are the siltstone. On top of that was laid the sandstone. So we know that the siltstone must have formed before the sandstone. We also know that both of those rocks have been faulted and folded. So these rocks must have existed before the faults and the folds happened. So we can put the siltstone followed by the sandstone first. We put it from bottom to top, just like the rocks go from bottom to top. So we will write, in geology, we'll write the oldest thing on the bottom and the youngest on top. The next thing that happened was either the folding or the faulting. And to tell which happened first, you want to see, has the fault been folded or was the fold faulted? It can be tough to tell looking at this diagram which of those is true. But it seems to me that if I'm looking at this, I see that this fault here has been folded by the same thing that has folded the rocks below. So to me, that suggests that this fault has been folded, which means that the faulting happened first and the folding happened afterward. Which way have the rocks been faulted? So is this a normal fault or a reverse fault that we're looking at? Looks to me like the motion is like this, right? Because we've got the siltstone that was used to be matched up here, but this part has been moved up and this part has been moved down relative to that. Same idea over here. So these faults are probably reverse faults. Following the faulting and the folding, the erosion cuts both the faults and the folds. This unconformity here cuts both of those. And then the very top layer is the basalt. So that's how you could look at this and figure out the order of these events. Today, we added in our understanding of faulting and of folding into that understanding that we can then use to interpret a lot of geologic history. Okay, that's our lecture. We've learned about the causes of metamorphism. We talked about the geothermal gradient, did a little bit of math with it to figure out how deep rocks are metamorphosing. We learned about different metamorphic rocks and their composition and texture and how it relates to metamorphic grade and foliated or non-foliated texture. We talked about metamorphic types and how different kinds of metamorphism exist in different plate tectonic settings. And then we learned about deformation with 2 types, brittle and ductile, and the senses of motion and the types of conditions that generate different types of deformation. Thanks for sticking with it. I'll see you next time.